Have you ever seen a beautiful picture of space, perhaps of a nebula or a galaxy, and wondered if the colors are real or how big it appears in the sky? Many pictures of the cosmos are abstract and seemingly far removed from our daily experience. The irony is that pictures of space, they capture that which is most common and ubiquitous. It is our daily life on Earth that affords us such a uniquely special view. You see, the problem is when looking at an astrophotograph, there are no people or easily identifiable references that help us to orient ourselves. Yes, the abstract form of a nebula can be beautiful without any further consideration. But if you were shown a picture of a person that was green, or perhaps they stood taller than a house, you would very quickly reassess what that picture was communicating. There's a similar kind of skill set that you can apply to the interpretation of astrophotographs, and that is what I'd like to show. So please come, join me on a journey through space and time and revel in the mysteries of the universe. We live in a world of images, and our digital lives rely on our ability to interpret them. It is a skill honed by countless hours in front of screens, big and small. However, some kinds of images, especially those that depict tremendous scales of size or time, defy our ability to easily interpret them. These images were not chosen randomly. They exhibit what inspires the most commonly asked question: what is the nature of the sparkles or lines that are emanating from the stars? Some people think that they were put there for artistic reasons. Others do not question their appearance in photographs because it perhaps meets an expectation of what a star should look like based on drawings or cartoons. These patterns are indeed artifacts produced by certain telescope designs. Reflecting telescopes that use mirrors have structures that hold secondary mirrors or other instrumentation. These rods or vanes obstruct a small amount of light that enters the telescope, and through a process called diffraction, the light rays are scattered. These so-called diffraction spikes are not desirable, and some form of diffraction always occurs with any obstruction. The images shown so far were produced by this telescope. This is the Schulman telescope, and it is the primary telescope at the UA Mount Lemmon Sky Center. This telescope is available to take images with, just like the ones you've seen so far. You can see the vanes that support the secondary mirror of this instrument. Notice how in this image, produced with a telescope that uses only lenses, there are no diffraction patterns. There are no obstructions to cause it. Most large telescopes use mirrors because it's not advantageous, or in many cases even possible, to build telescopes made only of glass lenses. This is why most professional images have diffraction patterns. On a more philosophical note, notice how the light of stars is spread into a spectrum of its colors. The diffraction of light into its component wavelengths is the primary way most astronomical measurements are made. Even though these are artifacts, the fundamental information is literally encoded in these images. It's as if the universe wants us to discover the answers if we only look hard enough and ask the right questions. Scintillating diffraction patterns are only but a superficial element of astronomical images. There are much deeper considerations of what is recorded in a picture. Typically, CCD cameras that are optimized for astrophotography are very sensitive and can record tens of thousands of discrete brightness levels. Computer monitors, by comparison, only display 255 grayscale levels. An astrophotographer must then choose how to represent and render the data recorded in an image. This is a picture of a wonderful spiral galaxy, and although its splendor is recorded in the data, those values are being rendered in its unstretched form with a monitor only displaying the very first few hundred brightness levels. By changing the white and black points, more of the data can be visualized. Now, we see a galaxy in the center with some spiral structure as well as a few other background galaxies. Finally, by representing the data in a non-linear way, the very faintest details are displayed proportionally brighter than the other parts that were already bright. However, even more of the story of this field is revealed. Now, we see the faint spiral arms as well as tidal tails of other interacting galaxies. When looking at an astrophotograph, keep in mind that the person who creates the image consciously decides this element of representation as well as many others, as we will see. Blend in the color information, and the image takes on new dimensions of life. Notice how I chose to display the very faintest and noisiest features as delicately hinted. This communicates that those features truly are difficult to see relative to the other elements of the image. The colors represented in astrophotography come in a few major variations. The images that you've seen so far in this video all record the visible wavelengths of light. However, this is only a small fraction of the electromagnetic spectrum, and astronomers pursue the entire span of energies that can be detected with instrumentation. With regards to the light we perceive with our eyes, even if looking through the largest telescopes in the world, the universe would not appear with the vibrant colors shown in these images. Our biology is simply not designed to detect these minuscule quantities of light. A full color image of visible light is created with a camera using filters that discriminates between reddish light, greenish light, and bluish light. These pictures are called broadband images, and when the images are assembled, the colors of light are mixed together in a way that is analogous to what our brains do. So in a picture like this, I do not choose that this should be blue or this other area be red. If your eyes were as sensitive as the camera that was used, and you could expose for as long, this is approximately what you would see. Sometimes people ask if an image such as this is enhanced in terms of its color. I take a different perspective and explain that it is our view of the universe with eyeballs which is diminished. If you look through any telescope in the world at this object, you would not see any color in this nebula. Yet, red and blue wavelengths of light would truly be hitting your eye. In this sense, then, this picture isn't an enhancement, but a more accurate portrayal of reality. And these instruments become our surrogate senses that allows us to understand the world around us. Another kind of color representation is done through narrowband imagery. This method captures light of specific wavelengths, which results in a high contrast image of nebular features. However, this isn't a true full color image because all of the other wavelengths of light are just not included. Here is a broadband image of the Eagle Nebula with the very famous pillars of creation in the center. These pillars were made famous by the iconic Hubble Space Telescope picture of them. The HST picture is a narrowband image. Note that the wavelengths that were used were only one green portion and two red parts of the spectrum. These then were mapped as red, green, and blue, resulting in a mapped narrowband image, which is an arbitrary color assignment. As you can see, the HST image of the Eagle Nebula is a small portion of a much larger object. This leads us to the important ideas of resolution and field of view. When looking at an astrophotograph, each pixel of a sensor detects light from a small patch of the sky. The size of this area on the sky determines the finest possible resolution of an image. First, a quick review of angular dimensions. A degree, perhaps the size of your fingertip held at arm's length, can be divided into 60 arc minutes. The moon subtends roughly half a degree on the sky, so it's approximately 30 arc minutes across. A crater on the moon might be several arc minutes in size. and an arc minute can again be divided into 60 arc seconds, so a bump on a crater on the Moon might be of this size. Taken together, the array of all the pixels determines the full field of view. The HST picture of the pillars is only a few arc minutes in dimension, whereas the field of view of the picture taken with the Schulman telescope is 10 times larger, though this is still smaller than the diameter of the Moon. There is something deceptive at play here, though. Each pixel of the HST image subtends a tiny 0.05 arcsecond squares of the sky, whereas a pixel in my image covers a patch of sky that is 6 times larger. Before I show a one-to-one comparison, there are some important rules of thumb to know about optical astronomy. First, stars are so far away that they are not resolved and are truly points of light. However, as light passes through our atmosphere, the rays are deviated by small amounts. We live in an ocean of air, and our view of space from the ground is blurry. Typically, this blurriness smears images by 1 to 2 arc seconds. Now we know enough to start interpreting images of all sorts. Let's begin with this wide-field image of the region of sky near the Orion Nebula. This image was acquired with this astrograph. Each pixel at the back of this telescope sees 5 arc seconds of sky. Recall that stars are points and the atmosphere blurs images by 2 arc seconds, which is smaller than 5. This means that the stars in this image look like little pixelated squares. The special name for this situation is called being undersampled. Now we overlay the region of sky captured with the Schulman telescope of the Orion Nebula and zoom in. Due to the increased scale, we can clearly see more details, and the stars are now blurred across many pixels. Finally, we can overlay the HST image and see things at its intrinsic resolution. The stars are nearly pixel-like and undersampled again. The fine details here are due more to the fact that the telescope is above the Earth's blurring atmosphere than it is due to the optics of HST itself. Did you notice that the HST picture is not a full-color image? One giveaway is that most nebula that have glowing clouds of hydrogen gas are pink or red. Other variations with multiple pastel hues are a good sign that the image is composed of mapped colors. Another thing to consider is that we now have 2 images with stars that are undersampled, both the wide-field image and the HST image. So how in general can you tell the difference? The easiest way to know is to look at the size of features of the object. If they are large compared to the field of view, it is most likely a large or space-based telescope image. Wide-field images will have small stars and also small details. Finally, no matter what kind of astrophotograph you're looking at, the stars in the image will appear to vary in their size. Stars are points, but all telescopes, even the ones in space, create images in which the light is spread out due to diffraction. The brighter the star, the more of the scattered starlight you see. So sizes of stars in a given image only signify brightnesses, not true dimensions. Take, for example, this wide-field deep image of Betelgeuse. This star actually fits inside 1 pixel on this sensor, but the bright glow of the scattered light can be seen to spill across hundreds of pixels. Let us use our skills to identify a few different types of images. First, we'll start with what might be a tricky image. This is a broadband image of one of the most colorful regions of the sky. Basically, each nebula type is shown here. There is red emission from glowing hydrogen gas near the star at the right and more of it in the lower left corner. The top of the frame is dominated with bluish scattered light from dust. This is called a reflection nebula. Finally, dark clouds of dust obscure the view, except where they thin, and then they show golden hues of light that filters through them, especially near Antares, which adds some of its own yellow-orange light. This is literally the palette of a large majority of diffuse nebulae. Can you tell if this is taken with a large telescope yielding a high-resolution image, or is this instead a wide-field image with undersampled stars and lower-resolution details? If you said this is a wide-field image, you got it right. This is a 4 by 8 degree region of sky. You could fit 64 moons in this field of view. Galaxies such as these are so far away that only our imaginations can span the distances. As such, when we look at galaxies, we see great averages of information. The combined light of stars and nebulae create low contrast details and colors because this light is mixed together. For this reason, it's unusual to see mapped colored images of galaxies, except perhaps for those that are our nearest neighbors. Here is a broadband image of M82 with an enhancement in the H-alpha emission that corresponds to the color of the red filaments of gas being expelled from this star-burst galaxy. The colors are the same without the enhancement, but by adding more signal for this particular feature, the added contrast makes the image much more compelling. When mapped colors are employed, the result is obvious and can highlight structures of galaxies. Here, radio wavelengths of light, mapped as blue, trace cool molecular clouds of hydrogen gas and show the skeleton of the galaxy. Here's what a regular broadband image of the galaxy looks like. This is a full-color image of what is effectively a narrowband object. It's a dying star that's lost its outer layers of gas. Our own sun may eventually end its life billions of years from now in a similar way. The sphere of gas fluoresces this characteristic blue-green color due to small amounts of oxygen in the nebula. This process always yields this particular color, which is why the HST picture of the same is an example of a mapped color image, with its expected extraordinary detail. Here is another image. Is this a mapped color image? How about the resolution? What kind of telescope likely generated this data? Well, this is definitely a mapped color image, and note that the details are quite large. The difficulty is that many images are not posted at their intrinsic resolution. Even an HST picture, shrunk down to some small size, can look like something a small telescope from the ground can do. But when the full image is shown, the image characteristics become obvious. Finally, how about this image? This is another mapped color image, but this time it really is a wide-field image taken with a small telescope. While the colors and resolution of an astrophotograph are generally image attributes that can be seen directly, many other aspects of processing that take place to produce an image are not obvious. Certain kinds of digital processing leave characteristic artifacts or other telltale signs. However, the important idea is that images of space are not snapshots. Raw data is typically dark, colorless, and perhaps even uninteresting. An astrophotograph, then, is the sum of hundreds of processing choices that are made to render the final image. Given the same data, different people will end up with different results. I would like to highlight just a tiny few such considerations to give a taste of what these decisions look like. When the initial raw data is displayed, it's possible to identify colors or details that are desirable to have represented in the final image. Many processing choices will blunt that effort or make it an even unattainable goal. Seeing the final image in your mind and processing the data in small methodical steps helps to stay on course. In this particular image, each of these features were observed early on, and with each processing step, they were maintained so that they could show up in the final result. CCD sensors produce linear data that exceeds a monitor's ability to be able to display everything at once, and so non-linear ways of displaying tonal variations are crucial. Without the use of high dynamic range algorithms, the interesting features of this galaxy, NGC 5866, could not be displayed. Note the inner disk with bluish tips and thin dust lanes, as well as outer distortions in the galaxy's halo. In fact, these kinds of decisions are not unlike what Ansel Adams would make when he adjusted the tonal values of his images. What interested him was not what he saw through his camera's viewfinder, but instead what he pre-visualized in his mind as a final image. He would then dodge and burn his film to achieve his vision. With astrophotographs, typically these adjustments are applied globally, or, if selectively, they are conditionally applied based on thresholds of brightness, color, and contrast. High contrast in particular is an image attribute that is preferred by both image makers and image viewers alike. There is an ancient evolutionary preference for high contrast, and this preference is shared cross-culturally. Adams, of course, knew this and played with it in his photography. The same lessons apply in astrophotography, but with some caveats. Take this image of the Trifid Nebula. Which version do you find most compelling? There's no right or wrong answer. These are simply just different choices. However, there are consequences for the choices that are made, and that is something to be appreciated. If you did not guess, my image is the one on the left. Although I could cater to the sugar high that contrast gives, I don't, because it comes with a cost. Light that filters through the clouds of dust has a subtle attenuation and depth which I feel is lost and flattened with the opaqueness that high contrast creates. To me, there exists truths in astrophysical objects, and I enjoy communicating as many as are captured in the data. For example, here are 3 images of the famous galaxy NGC 7331. This galaxy features wonderful dust lanes in its disk that reach all the way to the center. With particular processing choices, it's possible to display the dust lanes all the way to the core, clearly and distinctly. But to me, the cost is high. Galaxies truly are brighter in their centers compared to their outer disks. Maintaining this truth, and at the same time showing as many dust lanes as possible, that's my style. This means that although I show the dust lanes, they are more difficult to see in the center due to the lack of contrast. But to me, this is exactly what I would expect when looking at something very bright. In another example of the same sort, I processed this galaxy, NGC 4698, with my processing and then a version of high contrast on the right. But I prefer my final result on the left. I think it, again, better communicates the overall nature and features of this galaxy in a natural-like way. Here I stand in front of what at first appears to be a relatively nondescript picture of space, but one of the very best astrophotographs ever taken was of an object hidden within the inky blackness of this field of view. In fact, to appreciate just how superlative this picture was, we'll use some of the lessons that we've learned in this video, as well as find our place in the universe. To travel to the large distances that we need to, light speed is necessary. Light, in a particular unit of time, travels a particular distance. Take, for example, sunlight. It takes 8 minutes, approximately, for light to make it from the sun to reach us here on the Earth. So we say the sun is 8 light minutes away. Now, if we wanted to use the all too terribly small Earth-like units of miles, we can say that the sun is around 93 million miles away. But those numbers become unimaginably difficult to keep track of. Light units are much better and more convenient for measuring distances, large distances in space. Take the size of our solar system, and I'm going to be generous here and say the interesting parts of our solar system might be around 1 light day across. So it takes about a day, 24 hours, for light to make it from one side of our solar system to the other side. And what I'd like to do is create a model that allows us to appreciate how far away the nearest stars are, how large our galaxy is, and then where other galaxies are. I'm going to use something common like a penny to do that. So this penny, I'd like to squish our entire solar system 1 light day across into the size of something 1 centimeter or so across. A penny is a little more than a centimeter in size. But imagine this is about right. So you would have the sun at the center here with the Earth, all the planets, everything you know and love orbiting about this penny area representing our solar system. At this scale then, we can begin to imagine how far away the nearest star is. Its name is Alpha Centauri, and it's 4 light years away. Well, if this is 1 light day, then a light year is going to just be 365 of these. That's about 3 meters away, because each of these is a centimeter. So I need to do 4 times that in order to get out to the nearest star, and that would be roughly 12 meters away, a little more than 30 feet or so away. I think you can begin to imagine that if this is our solar system, already things are starting to become relatively large, because imagine you wanted to describe the size of our galaxy. We would only need to know 2 numbers. We just need to know how many stars are in our galaxy. That's how many pennies I would need to have in order to build the model at this scale. And we would need to know how large the galaxy is. Well, our galaxy contains more than, but at least, 200 billion other stars. So if I'm going to build a penny galaxy, I would need to begin with 200 billion pennies. If I had 200 billion pennies, I'd be a happy guy. That's a lot of money. There aren't that many coins in circulation in the United States, so this is in our imagination. And our galaxy is on the order of 100,000 light years across. So with that in mind, we can start to build a penny galaxy. We just need to know what is the average distance between stars. Our nearest neighbor is 4 light years away, but let's say that it's only 2 light years are necessary, so 6 meters or so. So maybe 10 feet to 15 feet or so is the spacing of pennies that I would need to set out to represent the stars of our galaxy. And I would do this one at a time. It'd take me a very long time. And spread it out until I've got an entire galaxy of pennies. How big would that be? Well, 100,000 light years across. If 1 light year is 3 meters, that's 300,000 meters. If we wanted that in kilometers, then that ends up being 300 kilometers in size. So, if our solar system is this large, our galaxy extends 300 kilometers in scale. And that's the beginning, to give you a sense of where we are, and then we would like to go beyond to consider where other galaxies are. Our nearest neighbor is the Andromeda Galaxy. It's located 2.5 million light years away. So if I continue with this model, I still end up by describing where other galaxies are off the Earth, even if I make our solar system only this large. The Andromeda Galaxy spans this image of nearly 4 degrees of the sky. If you were over there looking back at us, this is how we might appear, though I'd like to think that we have the better spiral arms. The stars you see in the picture are all in the foreground and part of our own galaxy. Zooming into the center reveals dust lanes that swirl all the way into the nucleus. Note that I was not too aggressive with the contrast in order to communicate the brilliance of the downtown galactic center. We live on the outskirts of what is the Virgo cluster of galaxies, the center of which is located some 40 million light years away from us. And that is what this is a picture of. This is a wide field image of that part of the sky that contains thousands of galaxies, though they're hard to see at this scale. You can see some of them, though. If you look in this general area, you'll notice some fuzzy oval patches. Those are all galaxies. And in fact, this general area is towards the center of the Virgo cluster. Let me turn on a label or annotated view of this region of sky, and I think that you can appreciate just how many galaxies there are in this particular field. Thousands of them. In fact, you can see somewhat of a gradient of galaxies going from this part of the picture on to over here, where it is much higher concentrations in this general area. So that gives you a sense of the number of galaxies, and I've been fortunate enough to have been given the chance to take pictures of many of the galaxies in this part of the sky. When you do so using a larger telescope, you're able to see them in much greater detail. For example, this is M100, probably one of the brightest and most beautiful of the nice symmetric spiral galaxies in the Virgo cluster. And when you show a large image of it, it really is a beauty to behold. Here is what at first appears to be a single little blob, but when you zoom in, you'll find that there are a pair of galaxies too, an elliptical galaxy as well as a spiral. My favorite galaxy in the view is M58, which is just, I think, an underappreciated spiral. You'll also find that there is M91 and M88, and those are also some beautiful spirals. Just a word about the spirals. You'll notice that as you go across the field, there are more elliptical galaxies in this area than where I've been pointing to where all the spirals are, because as the galaxies orbit closer to each other, they tend to mess up gravitationally, they affect each other, and they mess up those spiral patterns. It is in fact one of these elliptical galaxies, the largest of the Virgo cluster, that we will be venturing because that is where the monsters lie. We are going to be going to M87, and it is the location that we will find what I think is the very best astrophotograph ever taken so far.
Magnifying the image more from the Pomennus astrograph to the Schulman telescope shows that there is something remarkable coming out of the core. It is unlike anything else observed in the local universe. This is a relativistic jet of gas and energy that stretches for tens of thousands of light years. Zooming in more with the HST picture shows the detail in the jet and hints at the fact that there is something monstrous, something very powerful in the core of M87 to create this outflow. The only thing known in the universe that can create this much energy is a black hole. This is what has been assumed, but nary a single example ever directly seen, for decades. If you recall, each pixel of HST sees a tiny 0.05 arcseconds of the sky. If we zoom in to just a single pixel in this image and make it fill 1000 pixels on the screen, then the center single pixel is the size of the region captured by the Event Horizon Telescope collaboration. This feat required combining the light simultaneously captured from a network of telescopes that spanned the globe. Nothing less than a telescope effectively the size of the Earth could have had enough resolution to capture this region and directly observe the black hole at the heart of M87. This is a mapped or false color image in short radio wavelengths of light. Before the spring of 2017, pictures of black holes and magical unicorns were in the same category. We live in a time when a century-old question, one for which much ink has been spilled, is answered. Yes, there are black holes in the universe, and yes, much of the physics looks about right. The region shown here is roughly a light day in extent. Recall the penny for our solar system shown earlier. And it has the mass of around 6 billion suns. The image is as fantastic as the object it captures. It is the first of its kind, a one-of-a-kind, and an unbelievable astrophotograph to behold.